Okay, hey folks, picking up where we left off. And I'm going to talk about another example, another specific mechanism example. So last time I went through that, let's see, I went through the Lindemann-Hinshelwood mechanism, which is a general mechanism, but I use that specifically to talk about the bromine reaction. So we can apply this Lindemann-Hinshelwood mechanism to a lot of different types of reactions. So I want to apply that to this reaction with ozone now. Okay, and so what I'm going to point out is this is actually an elementary reaction right here. This O triplet P plus O2 plus M. So you can see more reactions involving third bodies. However, it's been proposed that even this elementary reaction can be broken down into some elementary steps. Okay. But the first thing that I want to talk about is this triplet P thing here. Okay. So that's called a term symbol. And as it turns out, O triplet P is a ground state oxygen atom. We're going to talk about this in a lot more detail in Chem 362. But this 3 right here, this is called a triplet state. Okay, so there's 3 main common occurring electron spin states that we encounter: the triplet, the doublet, and the singlet. Okay, so a triplet state is actually 2 spin up electrons. Okay, because if we look at oxygen's electron configuration, so let me do that real quick, right? We've got the 2s level, which we know is spin up, spin down. Let me erase that and start again. So then we know we have the 2p level for oxygen. Okay, 2p. And we know there's 3 vacancies. Oxygen has 4 p electrons, right? If we look at our periodic table, we can see oxygen, 4 electrons in the p block. So that's 1, 2, 3, 4. Okay, so these 2 unpaired electrons right here, that makes up what we call the triplet state. Okay, so that's the triplet. And so a triplet state, the reason why those 2 unpaired electrons are a triplet state is because there's 3 possibilities. There's both being spin up, there's both being spin down, and then in quantum mechanics, whenever we have an uncertainty of something, we apply what's called the superposition. We'll learn about that a lot more in 362. The superposition is this state that says, well, we don't know if it's up, we don't know if it's down, so it can be some, combination, like we don't know which electron is which, so we can't ascribe with certainty which is which. So that becomes 3 possibilities. Okay. As it turns out, when you have a paired up system like this, okay, 2 electron pairs, we call that a singlet state. And so oxygen, singlet D, we'll talk about what the D's and the P's mean when we get into 362, okay? So an oxygen singlet D is actually an excited state of oxygen. Oops, so that's the 2s level. So the 2s looks the same, spin up, spin down, okay? But now to create this system, we go 1, 1, 1, 1, and then actually what ends up happening is this makes an excited state with both of them getting paired up. And we call that a singlet state because that's how it exists. It can only exist one single way. Okay? So what this means is oxygen is a di-radical. Okay? So why is that important and why am I getting into all of this stuff? Okay? Well, when we look at this reaction of an oxygen atom with an O2 to form an O3, it seems like that should be a slam dunk in the chemistry, right? A singly unpaired oxygen atom is very unstable. It wants to bond with something, so it seems reasonable that this should not be a complicated mechanism. But as it turns out, it is, okay? So an oxygen triplet P, as we discussed, is a ground state oxygen atom, and it's a diradical, right? It's got two unpaired electrons, okay? As it turns out, and we'll see also examples of this when we get into 362, the O2 molecule itself is also a diradical. That's why it's paramagnetic, okay? So when these two things combine, an oxygen atom and an O2, they combine via this fishhook mechanism, right? By this radical mechanism, okay? And that forms an unstable O3 star. That's what that star means, okay? And it looks something like this, all right? We've got our lone pairs all around, okay? So, and then now we've got this elongated bond here with this other oxygen, all right? Okay, something like that. So this is really unstable. So this is our O3 star, okay, with that extra elongated bond. Right, the molecule hasn't quite formed yet, okay? So as it turns out, if we think about this via conservation of momentum, which we rarely think about in chemistry, but we should, if one oxygen, and so if the O triplet P and the O2 come at each other straight ahead like this, right? And they collide perfectly, we have to conserve their momentum. Well, as it turns out in this scenario where they collide with each other head on and they just are kind of coexisting close to each other, which is what this picture is showing, they have zero momentum, right? If they're both approaching from the opposite approach. So that would say that this unstable intermediate is stationary. It's not moving. Which at first you would say, well, shouldn't that mean it have zero kinetic energy? And you might think so because it's not moving, but it can't have zero kinetic energy because presumably this molecule is at like, room temperature or something like that. So all of that kinetic energy gets pumped into its vibrations, all right? And it's just as likely to kick right back out and reform that O triplet P and O2. So as it turns out, now this third body, so this is almost like the opposite, well, it is the opposite of what happens in the BR2. Now this third body right here collides with this unstable molecule and takes away some of its excess kinetic energy and allows the molecule to stabilize. And that excess kinetic energy is now given to the third body. So now the third body is in some kind of elevated excited state, which then it can quickly react and decay back to its normal state. So this mechanism, all of this just ends up looking like O triplet P plus O2 plus M goes to O3 plus M, right? And technically even it looks like the M just cancels even, all right? But what we could think of at first, we could put this together as DO3 dt equals K, and I'm going to use slightly different nomenclature. I'm going to say K Roman numeral 3, which I'll put up there, right? And so that Roman numeral 3 represents our third order rate constant. So K3 times O times O2 times M. So I'm going to drop writing O triplet P. Because as it turns out, if this was an O singlet D, if it was an excited state oxygen, even a third collisional body can't do it. So an O singlet D is just too reactive. And furthermore, if we think about this electron pushing, O singlet D doesn't have those available electrons that want to pair up, okay? So this gets really interesting. So this is why we use term symbols, so we can see the available electron chemistry, all right? So now what we're going to do, a similar thing as to what we did with bromine, we're going to analyze these mechanisms using the steady state approximation, and we're going to see how it all shakes out, all right? Okay, so, and in fact, one more thing to mention here, right? I talked about how this third body, it's the opposite of what happens with Br2, right? This, in the Br2 example, let's go back to this. Yes, in the Br2 example, we need a plus M to get that bond to break. However, look, in this scenario right here, okay, we need the third body to stabilize these two radicals reforming. So these third bodies or second bodies are very interesting, very dynamic in chemistry. Okay, so let's go for it. Let's put together this mechanism. Okay, so let's see here. So what I'm gonna first do, oops, I needed the reaction on this page as well. So I'm gonna analyze this whole mechanism right here, and I'm gonna do the steady state approximation on O3 star. Steady state approximation, because that is our unstable intermediate, all right? And I'm just gonna write the results. So I don't have the reaction written down up here, but I'll write the results. Actually, you know what, let's go ahead and do it. Let's say, if I recopy the mechanism, yes, it's an oxygen plus, yes, oxygen plus O2, Ka, Kb to make O3 star. And O3 star is stabilized by this collisional body at Kc and becomes stable O3 plus M star. And I'm not going to worry about M star decaying back to the ground state to M, because that process happens extremely fast. And when M is something inert, like a helium or something like that, its excited state doesn't matter. So we can ignore that. And that's why I don't even have a K for that reaction. Okay. So now, let's put together the steady state approximation for O3 star. Okay, this is more good practice. So we know that O3 star is formed as a reactant. Okay, so that means it's a positive rate. And that's going to be Ka times the reactants times O times O2. Okay, then now it can disappear for the reverse reaction. And so that's going to be minus Kb times O3 star, because in this reverse reaction, right now, O3 star is a reactant. Let's see here. And so that's 2 reactions involving O3 star plus a third reaction. So we need a third term. And now O3 star disappears at minus Kc times O3 star times M, and applying the steady state approximation says we can set that equal to 0. And so now, once again, we solve for what the concentration of O3 is using some algebra, taking that that's all equal to 0, right? I'll just do that for you really quick. So that becomes Ka times O times O2, all divided by Kb plus Kc, all times M. So this actually is shaking out to be very similar to the bromine situation, okay? And to make this easier, I probably could have used K1 and K minus 1 and K2, and you would have seen the results come out very, very similar. But all the same, I already made A, B's, and C's, so let's just go for it, okay? So now what we can say is if we look at the rate of DO3 dt, so now this is my stable product, okay? There's only one place that appears, and that's in this reaction, and that goes as Kc times M times O3 star. But we recognize that O3 star, that's an intermediate. We're going to have a really difficult time determining the concentration of O3 star. And in fact, it's only going to be around for, well, we're going to have a hard time determining its concentration because it's going to be around for such a crazy short time. Okay? So instead now, we're going to take our steady state approximation, right, and plug it in just like we did before. Okay? So now that's going to be Kc times M times Ka times O times O2 all divided by Kb plus Kc times M. And so now, once again, we want to think of this in terms of a high pressure limit or a low pressure limit, okay? So I'm going to continue on with this on the next slide, okay? So I'm going to rewrite this again, dO3 dt, so the stable ozone molecule, not the ground, or not the excited state, but the stable O3 product, okay? So I can rewrite that. So I'm just, using the same equation, but I'm just doing some algebra and writing it just a slightly different way, okay? So I'm going to write that as Ka times Kc times M, all divided by Kb plus Kc times M, all times O, all times O2. Okay? So this is actually pretty cool because in the grand scheme of things, when we look at this reaction, let me use this slide. When we look at this reaction and we think about, these unstable intermediates, right, and canceling it and getting some total reaction, okay? Our total reaction just looks like O plus O2 goes to O3, and I'll say that's occurring at a second order rate constant K2. Well, now look, I've got this reaction here, and look, this just the way I've written it in this form, it looks like O plus O2 goes to O3 reacting at K2. So in other words, all of this stuff right here just appears to be like a second order rate constant, right? Because I've got first order in oxygen atom, first order in molecular oxygen. And so all of this Ka times Kc times M divided by Kb plus Kc times M, it just takes on the effect of a second order rate constant, okay? And so I'll remind you that Ka is second order, Kb is first order, and Kc is second order. So this is a little bit more difficult to cancel things out and see how it all shakes out. However, we recognize because it's first order O2, all of this stuff has to be a second order rate constant. Okay, so now let's divvy this up once again into low pressure limit and high pressure limit. Okay, so let's look at the high pressure limit first. Okay, so in the high pressure limit, Kc times M will be much, much greater than Kb, okay? So again, if in the high pressure limit, M is very large, and when M is very large here, let's see, when M is very large, then that means now the way that this is going to go, because now this is slightly different than the bromine reaction, right? This O3 is stabilized by M to push it on and through to make that stable product, okay? And so now what that means is what we get here is the following. In this high pressure limit, now this value under here, right, because Kc times M is much, much greater than Kb, we can effectively ignore Kb. And now what we get is the following. It looks like DO3 dt equals. Okay, so if we are able to ignore KB, then we recognize that all of the KC and KM will cancel, and I just have KA times O times O2, right? And thus KA is approximately equal to that second order rate constant that just looks like an oxygen plus O2 goes to O3 without a third body, right? So in other words, in the high pressure limit for this particular reaction, the high pressure limit drives us to forming more product, okay? Which is pretty cool. That was the opposite of the example here in this bromine example, where in this case, the high pressure limit drives us back to more reactants. So these mechanisms are dynamic, right? High pressure limit and low pressure limit can mean different things for different chemistry, as you might expect. Okay? So let's see here. Where'd we go? So under the high pressure limit, yes, the reaction just approaches that of, I'm going to rewrite this under my high pressure limit right here. Okay, so it's just looking like O2, or O plus O2 goes to O3. Okay, so what about under the low pressure limit? Well, under the low pressure limit, okay, then M is very small, and thus now the opposite case, KB, is much greater than KC times M. All right, and so now under this reaction right here, what ends up happening is the following. Let's see here. So all of that ends up becoming DO3 dt equals. So now I can effectively ignore this KCM, right? And so this just ends up becoming Ka times Kc divided by Kb. Now all times M times O times O2. Okay? And so this is really cool. If we look at this here, in our units, a second order rate unit times a second order rate unit divided by a first order rate unit gives me a third order rate. So in other words, Ka times Kc divided by Kb just looks like this K1, 2, 3, which I described previously right here, right? So I'll write that reaction down again. So now under the low pressure limit, this just looks like O plus M plus O2 goes to O3 at rate constant K Roman numeral 3. Okay? So that is very cool. So we can see how these conditions manifest on specific reactions. All right? So now, and the final thing I'll say about this, let's see. I think I almost ran out of room. The final thing I will say, the way this all works out, all right, is as it turns out, Ka times Kc divided by Kb times M is very close to being K2. So Ka times Kc times M divided by Kb, it's approximately K2. All right, and so what that means is our effective second order rate constant, or really I should say, this becomes a pseudo second order rate constant when we consider that K123 times M basically just gives us K2. All right? Okay, so again, the pressure matters, the mechanism matters, as we go through and analyze our mechanisms, we can see really cool things where in some limits, all of those elementary steps are super important. Like for example, in this ozone reaction in the low pressure limit, that third body is super important. Okay. However, in the high pressure limit, it's as if that third body doesn't even exist. Okay. The reaction just goes O plus O2 goes to O3. Okay, so this is all very interesting stuff and mechanisms. Okay, great, folks. So that's the end of this video, and I will wrap it up with this brief section on mechanisms and elementary steps with a discussion of photochemistry. So that'll be the final lecture in this module. All right, folks, I'll see you in the next one.